Hey AP Calculus students, welcome back. Today we're talking about volumes. We're going to spend 2 days on this, and yeah, we're going to get good at it hopefully. So, um, those of you who are interested in physics, those of you who are interested in engineering and stuff like that, this volume stuff is super helpful. Um, yeah, so let's just jump into it. The idea of volumes are pretty easy. So, the volume is equal to the integral of a to b of ax dx. So ax is going to be the area of the base. Okay, so what we're trying to do here is think about it this way. If we're trying to find the volume of a cylinder, what we're doing is we're taking the base area, right, which is a circle, and we're stacking infinitely many circles on top of each other until we reach the top. Right, so just like we thought about our integrals as making tiny rectangles in there, in order to find a volume, we use the area of our base and we stack a bunch of those things up. Okay, so for example 1, it says a pyramid 3 meters high has a square base 3 meters on each side. Find the volume. So I have a diagram over here. So what happens is this is going to be at 0. This point at the base would be 3, right? And each of these squares inside is stacked up. And notice, because it's a pyramid, as we go from this side to this side, we're going to start from the tiniest rectangle on the top all the way till we hit our base rectangle, which we said is 3 meters by 3 meters on each side. Okay, so let's try to find the volume here. So we're gonna do this volume formula. We know volume is equal to the integral. I know that for my square, the side length is going to be whatever our x is. So I know that we're going to go from 0 to 3 because our biggest square is going to be 3 meters by 3 meters, right? And that's going to happen at the end. And then I know that the base is going to be x squared, right? The base, a square, the formula for a square is the side squared. And we're going to do dx. Okay, let's change colors here and do our integral. So this is going to be x cubed over 3, over 3 from 0 to 3. So then we plug in our 3. 3 cubed is 27 divided by 3 is 9. And then if we plug in a 0, 0 cubed is 0 divided by 3 is still 0. So the area, or the volume of this pyramid, is going to be 9 meters cubed. Okay, so pretty nice, pretty elegant. Now let's look at example 2. It says that the region between the graph f equals 2 plus x cosine x and the x-axis over the interval -2, 2 is revolved about the x-axis to make a solid. Find the volume. Okay, so let's go here and graph it. 2x cosine x. Is it plus x? Yeah. 2 plus x cosine x. Okay, so if we look at this from -2 is over here and +2 is over here, what we have is a shape that kind of looks like, oops, wrong one. Kind of looks like this. It's not very nice. So it looks kind of like this. From -2 to +2 for our x. Right, and what we're doing here is we're rotating it about the x-axis. So let's see if I can draw this. And each part of this is going to be like a circle, right? So we fill this up with infinitely many circles to find the volume. All right, so let's go ahead and do it this way. When we're doing ones that are revolved around the x-axis or the y-axis or some other axis, what we want to do is we want to set this up like this. So we know the top function is this. The bottom function is it's bounded by the x-axis, right? So we're looking at this. So each of these is a circle. So we need to represent the circle, right? Because we know that the volume is equal to the integral of a to b of the area, right? So let's figure out the area of the circle. So the area of the circle is pi r squared, right? So if we can determine what this r is in terms of our graph, then we can find our volume. Okay, so notice that the radius, right, for every circle is just going to be the height of our function. So it's going to be pi, and we're going to replace the radius with 2 plus x cosine x. And then we know our integral goes from -2 to 2. Okay, for this one, let me just check. They might be just asking us to find it using the fn int. Which they are. So let's go ahead and use our calculator for this one. Plug this in. Math 9 from -2 to 2 of, I should have put pi outside. I'll just multiply pi later. Okay, pi parentheses, actually let's do it here. Pi parentheses 2 plus x cosine x dx, and we get approximately 20. Did I do mine's weird? Oh, I forgot the squared. Right, we have r squared. Okay, let me redo it. Math 9 -2 to 2 of 2 plus cosine x x cosine x squared dx. And we get 52.43. There we go, 52.43 units cubed. Okay, so good practice in setting it up. And yeah, so that's one way, right? We stack a bunch of circles, and then we find the volume using circles because it's rotated around. So anytime we have a rotation, we're trying to figure out the areas for each circle and then do our integral of that. Okay, on to the next one. So this strategy is going to be washers. So let me just show you why it's washers. So basically a washer looks like this, right? There's a circle within a circle. So the middle part is a hollow part. So if we graph this one, it says the region in quadrant 1 enclosed by the x-axis and graphs of sine and cosine is revolved around the x-axis. Find the volume. So let's go back here and look at the graphs of sine and cosine. All right, so just in quadrant 1, the part that's bounded here, right, all the way until this point where they intersect. So they intersect at pi over 4. So we're going to make a note of that, right? We're looking at this area now. Let me draw it out here. So it looks like this, and like this. Something like that. And we know that this is pi over 4 for our x. Alright, so this thing is rotated about the x-axis. What's going to happen is we're going to have, let's change colors, circles, but these circles are going to have holes in the middle, right? As we rotate this around. So I guess if I drew a cross section of this, it would look like this, and then it would be hollow in the middle, right? That's not a very good representation, but you get the idea. So all we have to do in this case is we have to find the difference for each circle, for each washer, I guess I should say. All right, so we're still doing this whole idea of volume equals the integral of a to b of the area of x dx. Now the area, in order for us to find the area, all we're going to take is the big circle, and we're going to subtract the little circle. So for each circle, we're going to go from, remember this is 0, and this is pi over 4, right? So this is going to be from 0 to pi over 4. And we're doing, notice the cosine is on top, so we're doing cosine x minus sine x, right? That would be, the area is pi r squared, right? This would be our cosine minus sine. Actually, we should do this separately, right? Okay. Oh, pi r squared is good. Okay, so we should do this separately. So the big circle, right, would be pi cosine x squared minus the little circle, which is pi times sine x squared dx from 0 to pi over 4, right? We wouldn't want to do the subtraction first because that would give us a weird radius, and we're not trying to find like the radius of that circle. We're trying to find the outside circle minus the inside circle. Okay, so let's go ahead and do this. They're saying that we can do it using an identity. I mean, I guess we could do this, or we could use it our calculator. So let's just go ahead and use a calculator because we don't need to remember these identities in order to solve. I mean, we could, but then I don't think it's gonna help us that much anyway. So let's go ahead and do this in our calculators. So from 0 to pi over 4. And we're doing pi cosine x squared minus pi sine x squared dx. And we get 1.570. So 1.57 units squared. 1.57, this is going to be also pi over 2 units squared. Okay, so these are equivalent. Either way is nice. It's fine. Okay, so that's washers. So if we have a solid with a hole in the middle, we're going to use the washer strategy. And we just take the big circle, the outside circle, minus the inside circle. And we should be good. I guess that's it for today. So good job. Quick refresher, if we're trying to find the volume, we're going to do the integral of the area of the base. So the first one we did was not rectangular, but a square base. And that turned into a pyramid. The second one was the rotational solid, right? So we took the graph and we rotated around one of the axes, and then we filled it up with circles. So in that case, the circle was the base. And in the third one, we're doing washers. So we had circles with the circle cut out in the middle. And in that case, we did the outside circle minus the inside circle and found the integral of that to find our volume. Okay, we're going to continue this tomorrow or next time. So good job today.